Hello, this is Hyunji Moon from Seoul National University. My major is Industrial Engineering, and I am a current manager of StanCon Korea, and also the founder of startup NextUp, whose mission is to provide affordable but advanced analytic tools. This talk introduces how I and my two colleagues, Jinwoo and Hyeonseop, developed hierarchical spline model to predict engine failure of 99 naval ships in Korea. Before starting our journey, one thing to note is that ship failure in a naval setting has many causes, but in this study we focus on only the failures caused by engines. The contents are as follows. Two characteristics of our setting motivated our study. First is a hierarchical system. There are about 150 battleships in Korea, and those battleships could be categorized according to their engine types. Our train set consists of 99 ships with 5 types of engine. We discovered that ships with the same engine type display similar failure patterns, and also not all engines are created equal. Based on the engine's date of birth and successor-predecessor relationship, different degree of closeness between engines are discovered. As you can see from the left plot, out of 99 ships, we have different composition of engine types. So for example, for engine type 3, there are 43 ships that has engine type 3. And this leads to our second motivation, unbalancedness and missing data. So maximum ship's lifespan is 31 years. Our ultimate goal is to predict how many failures are expected given on information of a ship, its engine, and age. Therefore, we need to construct a failure function of an entire lifespan of a ship, not just part of it. However, as you can see from the plot, which shows failure count for each ship at its certain age, data are highly unbalanced for two categories. First, engine types, and second, their age. This imbalance and the fact that 80% of our data are missing obstruct the use of many existing time series models, such as ARIMA. Data from multiple categories should be combined systematically for our problem setting. I guess most of you have experienced at least one of these problems in your own domain. Problems we faced while predicting naval ship engine failure are general, and we believe our attempts could be applied widely. The example being other military systems such as tanks or battle planes, which will be discussed at the end. Based on the two characteristics, we chose Hierarchical B-spline as our model. The figure and equations show how each layer is constructed. Subscript S and E each stands for ship and engine. The last equation shows how the mean failure count are designed. Intercept alpha and basis function weights W are two main parameters for our model. B represents basis function in the right plot. If you move up to the second layer, ships with same types of engine share hyperparameters. And if you go one more layer up, all engines share 4 hyperparameters: alpha 0 bar, sigma alpha bar, W0 bar, and sigma W bar. And these are the hyperparameters which correspond to the engine archetype. Several considerations remain even after completing the model backbone. The priors. When exponential 1 was given to all sigmas, we faced two problems. R had over 4 for some parameters, and unmatching Y replications and Y, as you can so evidently see from the top figure. The figure shows that the observed Y, which is a black line, is highly different from the posterior predictive Y repetition. We were in despair for a while, but proceeded on fixing the model. Stan User Guide was a great help in this process, and we came up with 3 solutions. This gave us hope again. We applied Box-Cox transformation to Y, which is known for its effect of massaging the distribution to normal. And also, we applied non-center parameterization and changed some priors, for example, gamma 4.4, 0.25. And these are all performed based on the predictive checks. These are the results for hierarchical spline model, which I will refer to as HS from now on. From the model, we can retrieve a total of 105 splines, 1 for engine archetypes, 5 for each engine type, and 99 for each ship engine. Data is scaled due to security issues. Note that hierarchical model helps us to fill out missing X values in our problem setting ages from 1 to 31, while decomposing Y values, the failure counts, into 3 layers. The left plot is full HS model results, and there are a few things to note when compared to our baseline model, Prophet and ARIMA. First, as 80% of our data are missing, lifespan failure functions are not robust for both models. Blue line in right plot shows failure count predictions corresponding to engine type 1 to 5. For example, engine type 3, which had its data concentrated on the old ages of an entire lifespan, cannot predict its early ages properly in Prophet model. For ARIMA, the prediction itself was very difficult as imputation was not applicable for our setting. This shows that HS gives robust failure prediction of an entire lifespan, which is our ultimate goal, compared to 2 other baseline models. If we dive deeper into prediction, there are 2 different scenarios. New ship with engines included in our train set, and new ship with unforeseen engines. Different models should be applied for these scenarios. In the case of hierarchical model, these differences are evident by comparing the top 2 equations. First 2 layers, engine archetype and engine layer, could be used in the first scenario. But for the new engine type scenario, the information we have only comes from the first layer. And we should go all the way to eta, the hyperparameter that represents the engine archetype, in order to predict the failure counts. For Prophet and ARIMA models, they are constructed based on the average time series of each engine for the first scenario. And for the second scenario, the average time series of 99 ships are used. Each scenario predictions for each models are represented by blue lines and red lines from the two plots. Errors are compared for train set and test set with two scenarios. For Prophet and ARIMA, same model are used for the first two cases due to unreliable predictions from lack of data, which I have discussed before. Stark improvements are observed in train set, and especially for categories with enough data. Engine 3, which had 43 battleships. Low performance are observed in new engine settings, where HS could use only the first layer of information. As you can see from the table, ARIMA performs better in case of new ship and new engine setting. Model for new engine need to be more clever. But how? There weren't any quantitative information. But we know the relationship between the engines, such as date of birth and successor relationships. For example, century of birth, out of 5 engines included in our test train set, engine 2 and 3 was born in 20th century, while engine 1, 4, and 5 was born in 21st century. And successor and predecessor relationship. So for example, engine type 5 is a successor for engine 2, and so is engine 4 the successor for engine 3. So we thought that this prior knowledge between the engines could be applied to deliver the information for the newly unforeseen types of engines. As we know the date of birth for new types of engine and whether it is a predecessor or successor to the existing engines that we have in our train sets. So from the equation in the left top, you could see that from the second line, if this term, new engine posterior, we decided if this term could be substituted or re-expressed with known posteriors of engine 1 to 5, we could deliver the information that we have on the engine types and therefore enhance the accuracy of the model. Hypothesis was set that if the output from the learned model are consistent with our prior knowledge on the relationship between engine 1 to 5, this approach is reasonable. And we have conducted the experiment. And based on the learned models, we discovered that construction error has a big effect on the engine failure. Distance between each failure function indicates that engine types 1, 2, and 5, which are constructed in 21st century, are relatively close to each other. Successor and predecessor relationship was also interesting as their functions had similar shape, the only difference being their intersects. The bottom plot shows the engine pair 2, 5 and 3, 4. Therefore, based on this observation, we expect that the framework that could quantify this qualitative information could enhance the model greatly. To summarize, hierarchical spline model could have 3 large advantages. The first is it could reflect hierarchical dependence in engine failure system. And it could construct entire lifespan function, even though 80% of our data are missing. And lastly, it could provide interpretable results for the effect of each layer. Last is further development. 3 big directions are possible. The first is we could diversify our models. This can be carried out by either changing the data generating process itself or just the prediction target. For example, Gaussian process model could be developed that forecasts the failure count of each year, and the right plot is the result of the Gaussian process. And you could see that the results are highly similar to the results from HS model and also the real data. Another approach is to change the prediction target. For example, in the HS model, the forecast target was failure count per year, but we could predict time to failure instead. An example of the model could be using Weibull cumulative distribution function to forecast the time to failure. The last approach is to parameterize missing data. So this was introduced in the Stan usual manual, but I wonder whether this approach could improve robustness in our setting as well, where majority of our data are missing, where more than half of our data are missing. So I wish to get some feedback from you. The second is Bayesian model averaging. We have designed several models and also the features, in other words, the second layer engine types could be replaced with other traits such as ship size. And these various models could be designed, and in order to enhance the accuracy, we could design a framework that could combine the predictions that leads to a more robust predictions. Package Lu in R and package rvig for Python supports this Bayesian model averaging. And the last one is domain extension. Current prediction for repair parts could improve greatly in terms of its accuracy according to our interview with military expert. And considering the military scale in Korea, which has around 5,000 battle tanks or 200 battle planes, enhancing the accuracy could save at least $1 million per year. And apart from the military equipment system, systems that includes interdependent time series or hierarchical structure are also our interest. The last slide is to introduce Stan Korea community. I have launched Stan Korea community after attending 2018 StanCon. So our community is 2.5 years old, and we have held many meetups and study groups. Recently, I and 7 other members have published Korean BDA. We also have our own YouTube channel where my Stan Korea partner Hyeonseop uploads Stan-related contents on a regular basis. We have over 300 subscribers, half the size of official Stan YouTube channel, which I am very proud considering the population proportion. Please join us if you are interested. Thank you for listening to my talk, and I would really appreciate your valuable comments.